Hello, welcome back to Short Lectures in Physics. And the topic for discussion in this session is superposition of light waves and introduction to interference of light. It is known that light is an electromagnetic radiation traveling from a source in all directions through a medium with uniform speed. Speed will be different for different media of its travel. As already we know about reflection, refraction, diffraction. Now we are introducing the interference and next go to diffraction principles. The ray optics principles, though they are able to explain the reflection, refraction, or dispersion, etc., but interference phenomena cannot be explained through the ray optics principles. So the wave theory of light has been introduced to explain the other phenomena like interference, diffraction, polarization, according to which the disturbance from a source of light causes the particles in the medium to vibrate up and down perpendicular to its direction of travel from the source. The disturbance travels as transverse waves and they are in the form of a sine wave. Particles in the medium will be in phase. That means if you place one over the other, trend will be in the same. That means the wave, both waves will be going up at the same time or they will be going down at the same time. The position of the particles for both waves will be same. The waves are said to be in a phase. So particles in the medium at same distance from a source of light will vibrate with same phase. As light is traveling in all directions, all particles vibrating in the same phase will form a locus, and locus of all such particles vibrating in phase is called a wavefront. The lines perpendicular to a wavefront indicates the direction of the light travel, and they are called light rays. Wavefront is of three types, depending on the source of light. In case of a point source, the light travels in all directions and the particles at the same distance from the source will be in phase beside. So the locus of all such particles in phase will form a sphere in three-dimensional space. The locus of all such particles in phase will be in the form of a sphere and it is called spherical wavefront. So spherical wavefront is one form. Cylindrical Cylindrical wavefront is another form which can be visualized for the light coming from a linear light source. That means like a tube light. The light travels in all directions from that linear source and the wavefronts will be in the form of a cylinder. Length of the source being the core of the cylinder, hence called cylindrical wavefronts. And as we move away from the source, the wavefronts looks like a plane, hence they are known as plane waves. Most of the times we describe the light phenomena in the form of plane wavefronts. That means all the wavefronts from different distances will be parallel to each other and the light rays are also parallel to each other, perpendicular to the wavefront, plane wavefronts. That's only possible when we consider the light phenomena at faraway distances from the light source. The amplitude of the disturbance varies from its mean position to a maximum value. The maximum value is known as the crest of the wave. Then it reduces to mean position and again increases to a maximum value in the negative direction, that is opposite direction. It can be negative or it can be positive or it can be zero depending on the type of the wave we are considering. The minimum position in the opposite direction is known as the trough. Later again it increases to the mean position. Starting from a mean position going to maximum position in the one direction and then coming to mean position, again going to maximum position in the reverse direction and then coming back to mean position. This comprises of one full wave, and the time taken by the wave to complete one cycle is known as time period T. And frequency is the number of waves passing through a point in 1 second. So if T is the time taken by the wave to complete one cycle, then the frequency will be inverse of T, that is 1 by T, and its unit is per second, that is s to the power of minus 1. Distance between two successive crests or troughs of a wave is called wavelength. It is denoted by lambda. In terms of frequency and wavelength, the velocity of the wave can be given by v is equal to f lambda or lambda by t, and in case of light its value is 3 into 10 to the power of 8 meters per second. Note that the waves are characterized by its frequency and wavelength. Having known about a wave, now if two such waves meet, it results in a different wave following the superposition principle. According to the principle of superposition of waves, when two or more waves traveling in a medium meet, they get superimposed and result in a new wave whose amplitude, denoted by y bar, a vector quantity, is given by the vector sum of amplitudes of all waves involved at that particular time. Thus y bar is equal to y1 bar plus y2 bar plus y3 bar plus up to yn bar, depending on the number of. Most of the times we consider two waves in our simple studies. So y bar is equal to y1 bar plus y2 bar. The amplitude, also known as the displacement of the particle in vibration of a wave, it is a function of time and space. Superposition principle, whatever we mentioned, holds good for all types of waves in light studies, acoustic studies, mechanical studies, surface water waves studies, radio waves, gravity waves, electromagnetic waves. Now consider two harmonic waves with the same frequency, hence wavelength, meet in a given region. Their amplitudes can be same or different. They can superimpose one over the other depending upon their respective displacements at a given time. In this slide you can see two waves of different amplitudes y1 and y2 are superimposed one over the other such that they are in phase. That means the first wave and second wave both are increasing in the first half time period and decreasing in the opposite direction in the second half period. Both the waves are increasing in the positive direction or increasing in the negative direction, and the crests of both waves as well as the troughs of both waves are occurring at the same time of instance. In such cases, these waves are said to be in phase. Then the amplitude of the resultant wave is given by the sum of the individual waves. Thus, y is equal to y1 bar plus y2 bar. The resultant wave is also shown in the slide. The waves are said to be out of phase if the crest of one wave and the trough of the other wave occur at the same time as shown in the figure. Then the amplitude of the resultant wave is given by the difference between the amplitudes of the two waves, that is y1 minus y2 or y2 minus y1 depending on the magnitude. So the resultant wave is shown as y bar with the red line in the slide. When the two waves meet depending upon their superposition, there exists a phase difference and path difference. The phase difference is given in angular units while the path difference is given in distance unit. Both are obtained from the relative positions of the two waves in a given time with reference to an initial reference point. For example, the y-axis indicating the amplitude is shown in the figure. The first wave is starting at the time t is equal to 0, and the second wave is starting at time t by 4. So there is a time difference between the two waves at any point, at any instant of its motion is t by 4. So for the situation shown in the figure, the time gap is t by 4, hence phase difference is pi by 2 radians or 90 degrees, and, and hence the path difference is lambda by 4. Here it may be noted that the time taken for the one full wave is t, and the distance traveled by the wave is wavelength lambda, and the angular displacement is 2 pi radians. Because in the present situation the time gap is t by 4, hence the phase difference becomes, that is 2 pi by 4, that is becomes pi by 2 radians, or 360 by 4, that is 90 degrees. Similarly, path difference x is given by 1/4 of the lambda, that is lambda 4. Now consider another case in which the time gap is half the time period t by 2, hence the phase difference becomes pi radians or 180 degrees, and the path difference x becomes lambda by 2. In this case, the crest of one wave and the trough of the other wave are occurring at the same time. In time t, one full cycle is completed for any of the waves, during which the angular displacement is 2 pi radians and the linear distance is 1 wavelength. So if the time difference between two waves is small t seconds, then path difference is equal to t by t of lambda, or t by t is equal to x by lambda. The phase difference phi is equal to t by t 2 pi. Thus phase difference, if we substitute t by t is equal to x by lambda from the path difference equation, then the phase difference phi is equal to 2 pi by lambda times the path difference x, or path difference x is equal to lambda by 2 pi times the phase difference phi. This is how we can calculate the phase difference and path difference of two different waves meeting in a medium at a particular time. When two in-phase waves with same amplitude superpose such that their crush or troughs occur at the same time, it results in a constructive interference. They interfere together to result in a different wave. Then the amplitude of the resultant wave will be maximum and is given by the sum of the amplitudes of the both waves. As shown in the slide, wave 1 and wave 2 both have amplitudes y. They are in phase, that means their crush are occurring at the same time, 1/4 of the t. Their troughs are occurring at the same time, 3/4 of the time t. T is the time period of the wave. Then the resultant wave crest also occurs at 1/4 of t, and the trough occurs at 3/4 of t, but the amplitudes will be 2y in both directions. The amplitude is double, but the frequency is same. Hence the path difference and the phase difference will be 0 in the present case. Remember that both waves are in phase and have same amplitude. This results in constructive interference. When two out-of-phase waves with same amplitude superpose such that crest of one wave and the trough of the other wave occur at the same time, then it results in destructive interference, because the amplitude of the resultant wave is 0 as given by the vector addition of the amplitudes of the both waves, that is y minus y is equal to 0. Hence the path difference between the two waves is lambda by 2 and the phase difference is pi radians or 180 degrees as shown in the figure. Interference refers to superposition of light waves generated from two coherent sources. Remember that these sources must be coherent. We will explain what is. Waves from the sources will be in phase, hence they possess same frequency, wavelength, and amplitudes at any instant of time. It results in interference fringe pattern at some distance from the source, and the pattern comprises of equally spaced alternate bright and dark regions of equal width. The central fringe will be a bright one because of the zero path difference or phase difference. All bright fringes will have same intensity while the dark fringes will have zero intensity. The typical interference pattern is shown in this slide. Two light sources are said to be coherent only if they possess same frequency, hence wavelength, and zero or constant phase difference. Examples are a light coming from a laser source. The light must be coherent and generated from a point of monochromatic light source to achieve an interference pattern with a better contrast. Monochromatic is light source having one color like red laser light, and nearby light sources provided a wide interference pattern. Screen should be far from the source. The light generated from a monochromatic source is shown in this figure, and the light is allowed to pass through two slits S1 and S2, which are closely spaced and finer in dimensions as far as possible. Then the incident beam passes through the two slits S1 and S2 such that the light wave fronts travel in forward direction as shown from S1 as well as S2. They interfere. When they meet, there will be situations where the two waves will be producing the coherent interference as well as destructive interference. Depending on the path difference and phase difference by the waves reaching the screen in that time interval, the path difference and phase difference will be different to reach the screen at any point in the vertical direction. Depending upon the path difference and phase difference of waves coming from S1 and S2 at the screen at different points vertically above and below the mean position, they interfere either constructively or destructively, thus produce bright and dark fringes. They are called fringes. They are equally spaced and width of band is same and the amplitudes will be same. This is a typical interference pattern. The more details on interference will be discussed in the other session. Hope this gives a clear understanding of the superposition principle and some basics about interference. See you. Bye.